Swayam Prabha. Digital India. Educated India.
It's going to be just broad, general, and overview of CCUS per se, CO2 capture, utilization, and storage or sequestration. And then we'll talk a little bit about the specific work that we do. First part, maybe I'm going to make a few controversial statements, but so be it. If you have any questions, if you want to interrupt me, please feel free, raise your hands. I'll be happy to take any questions at any point that you have. You don't have to wait until the end of the talk. I don't need to go through all the slides, okay? I would rather this be more of a dialogue and a conversation rather than me just presenting bunch of slides. Okay, so some facts to bust some myths and misconceptions or to set the stage, as the case might be. First, CO2 is not a pollutant. CO2, unless it completely replaces oxygen, is not going to kill us. Okay? Pollutants, for example, carbon monoxide is a pollutant. Really small amount of carbon monoxide, 100 ppm level, will cause a lot of headaches. 0.1% of CO2 is super dangerous. Not CO2. Okay? CO2, you can have a good amount of CO2, and the only time it really becomes dangerous is when CO2, which is usually the product of combustion in dangerous situations, that replaces oxygen. That's when it becomes really dangerous. Otherwise, CO2 is not a pollutant. That doesn't mean it doesn't have negative effects on environment. It does, but that's a greenhouse gas. Greenhouse gases are not necessarily pollutants. Okay? If you burn any carbon based fuel, okay, the best thing that you can do is convert it into CO2 and water. Anything else is less efficient. Anything else will result in pollutants. Okay? So, the other way of looking at it is, if you have a fuel, how much is the net efficiency of that overall process? You try to maximize the efficiency, you will maximize profits, and that's a different way of thinking about how to minimize CO2. Okay? The other aspect of it is, the more carbon you have, more amount of CO2 gets released in order to give heat which can be utilized. Okay? So therefore, methane, which is CH4, has 1:4 ratio of carbon to hydrogen atoms. Coal is 1:0 ratio of carbon to hydrogen atoms. Okay? That's one of the challenges with respect to coal. The other challenge is that coal combustion is less efficient than combustion of gaseous fuels. Okay? Now, how much CO2 we are adding into atmosphere? We are adding just 2 ppm of CO2 every year, just 2 ppm. But it's not just. Why? Because our atmosphere is huge. It's really, really vast. So 2 ppm corresponds to 40 gigatons or 40 trillion kilograms of CO2 per year. That's a huge amount of CO2 that is getting generated. Half of that is getting captured. Okay? Half of all of the CO2 that we generate is getting captured, but only 2 gigatons, okay, 2 out of 40 gigatons is because of human intervention. And most of it today is from forests. Okay? So, we are capturing approximately 0.05 gigatons of CO2 through various different ways, CO2 capture, CO2 sequestration, blah blah blah, that you talk about. Okay? So now if you want to go from that level to be able to capture a large part of our CO2 emitted, it's a very large challenge. It's not an easy problem. it is going to have economic consequences also, and you cannot say that economic consequences, they can take a back seat. Okay. For example, India has a fairly large proportion of coal based electricity supply. We are not going to start reducing our dependence of coal until 2040. Okay, but we are also a developing nation. Okay, so I don't buy into the argument saying that the developed nations have emitted for last 150 years and or more during an industrial revolution, so now we have the right to do so. No, I don't agree with that. However, no, we don't really have a choice. You cannot tell 1.4 billion people that what, in some distant future our economic problems and electricity problems will be taken care of, let's only go behind CO2. We don't have that luxury, if I can use that word to say that. Okay. So why I'm saying all of this is because when we talk about difficult problems, challenging problems, they are challenging because there is a compromise. Okay, and it's the compromise that makes it really challenging. Okay, do we have the technology to get rid of all CO2? Maybe we might. Okay, but the question is, do we have the technology to get rid of the CO2? Okay, in a reasonably economical way? I don't believe so as of today. Okay, that's the reason why India has a net zero target of 2070. Okay, it is about walking through or wading through these compromises. Paris Accord, 1.5 degrees Celsius, we are not going to meet that target. Okay, that's the fact. I mean, we can still say that, oh yeah, it is possible to meet the target and so on. No, we are not going to meet it. Okay, does that mean that we do nothing? No, it doesn't mean that we do nothing. It means that as engineers, okay, we understand the compromises that are involved in tackling these challenges. These are also challenges that cannot be tackled by one set of individuals. It cannot be tackled by a few universities. It cannot be tackled only by chemical engineering department, for example. It will need to be a work between chemists and chemical engineers, material scientists, mechanical engineers, physicists, everyone involved. Okay, and that is why some of the interdisciplinary work is going to be even more important than what it was in the last 100 years. Okay, so that's if you broaden the perspective rather than just talking about CCUS and so on, that's how I would like us as engineers to think about these overall problems. Okay, petrochemicals is not a conspiracy. That's my view, that's my personal view, not necessarily representing IIT Madras's view. I should make that statement unless I get into some trouble. Why? Is look at the fuel. So what we are plotting over here is the energy per volume and energy per kg. Okay, if you look at, for example, hydrogen, okay, your energy per kg is very high, but energy per liter is very low. Okay, on the other hand, if you look at aluminum batteries and so on, or zinc air batteries and so on, they have a very large volumetric capacity. Energy per unit volume is very large, but energy per unit mass is very small. Okay. On the other hand, liquid fuels like petrol and diesel, see where they very comfortably sit. They very comfortably sit at the location where both energy density gravimetric and energy density volumetric match. Okay. Do you have any idea what typical fuels are used in rockets? Hydrogen and oxygen, aluminum powder, solidified hydrogen. Okay. Why do you use solid fuels? Volumetric density? Why would you use solidified gaseous fuels? Okay, you use gaseous fuels because high gravimetric density, you make them into solids to get high volumetric density. Can you do that in your car? Quite difficult. Okay, not impossible. You can still have cryocompressed hydrogen in a vehicle, and you have Toyota Mirai that carried hydrogen at 700 bar pressure. Okay, we can carry hydrogen under high pressure and liquid nitrogen temperatures of 77 or 80 kelvins. Yes, it's possible to do that, but again, coming back to what I said a couple of slides earlier, compromises. What you gain by reducing the weight and volume that you carry in your vehicle, you lose by the energy that you need to expend in cooling that gas to 80 kelvins or compressing it to 700 bars. Okay, so it's not a silver bullet solution that this is what solution is going to work all the time. Maybe in future there might be, I don't foresee it as of today. Okay, doesn't mean solution doesn't exist. It's multiple solutions, and each solution is going to be local as well as temporal. What is valid today, 10 years later may not necessarily be valid. Okay, but while I said that petrochemicals are not a conspiracy, we do emit a lot of CO2, and fossil fuels do carry a fair share of blame for it. Okay, solar and wind are great, okay, but it is not free lunch. We have a lot of statements I've heard, and yeah, I continue hearing, sun shines, it's just free. We had cyclone, so much amount of wind swishing around, just capture that wind. If only life were that simple. Okay, we need equipment to capture energy, we need equipment to store energy. Silicon wafers to get the crystalline silicon, we need to go 300 degrees Celsius hotter than what you need to make steel, and steel is a hard to abate industry, silicon is harder to abate industry. Okay, where do we gain? We will gain if you make a little bit of silicon and or whatever the solar panels might be, and use it for a couple of decades or longer. Okay, but they do have an environmental footprint. All of the solutions do also have environmental footprints. As engineers, we should not be blind to that environmental footprint, and that's what brings me to this word NIMBY, not in my backyard. Okay, we are all not in my backyard environmentalists. Okay, as long as my car is not emitting the gases, I am completely unaware of the overall impact. Example, electric vehicles in India. If we have a lot of our energy coming, a fair share of our energy coming from coal fired power plants, having an electric vehicle might actually be worse for the environment today. Does this mean we should stop manufacturing electric vehicles or buying electric vehicles? It reduces the local pollution, but overall if you look at the LCA, today it is not, right? But if we wait until 2040 till the coal fire power plants start decreasing, it might be too late to introduce electric vehicles then, right? So I am not saying no electric vehicles, okay. Again, what I am saying is compromises, and as engineers we should be aware of these compromises and not think that this is the best and I have gotten rid of all the problems and so on and so forth. Okay, we are sometimes not aware of what NIMBY environmentalism does. What NIMBY environmentalism does sometimes is you get rid of that guilt in doing bad to the environment, and then you inadvertently end up doing a little bit worse. Now, I had a friend who who has all the very, I mean, he buys 4-star and 5-star energy rated gadgets, whether it is washing machine or and so on. I mean, you have, I think there is a Siemens 4-star washing machine that costs 1.2 lakhs or something like that. Okay, he has that. Why? I want to do something for the environment. He had a 2-bedroom house. Now he has a 5-bedroom house. In northern United States, the gains that he has had by going to this 5-star equivalent is completely washed out by the amount of heating that a 5-bedroom house is going to take. Okay, taking this person is not actually my friend, I am making a fictitious example, but anyway, the reason why I say that is this is not a fictitious example. We do this all the time in our lives. As engineers, let's be aware of that. Okay, let us doing 2% good, let it not give us a blank check to do 5% bad. Okay, so that's the point I want to put. Very different than that a technical aspect, but I can't say this type of a thing to a general audience. Why? Is because general audience is not sometimes equipped to understand nuances. The moment you say that, you know what, yes, that's why global warming is not real. No, global warming is very real. We have literally from 2015, we have had 2 cyclones at least every year. Okay, the increased cyclonic activity may quite likely be the effect of global warming. Again, the use of word may is something that is not very well understood by people because people don't understand uncertainty or probability very well. Okay, we also don't understand probability, but maybe a little bit better than lay people. Okay, so as engineers, I think it's our responsibility to put what we do and the solutions that we bring to the table in a broader context. Okay, and one thing I would really like to emphasize is humility and not arrogance, and that's really important. These are large challenges and it requires us to work together in a collaborative way, in an interdisciplinary way, in order to tackle some of these challenges. Okay, so some of these slides were for audience containing undergraduate students who are interested in PhD. So it was geared towards telling them, what, these are interesting challenges, and we have faculty in chemical engineering, chemistry, physics, civil engineering and other electrical engineering, all of them working on problems like this. And these are the various people, as just wearing head of the department hat for a minute. These are the various faculty in our department working at the interface of chemistry and chemical engineering, of physics and chemical engineering, of material science and chemical engineering, electrical engineering and chemical engineering, mechanical engineering, chemical engineering, math, data science, AI and chemical engineering, aerospace and mechanical and chemical engineering, and civil, environmental and chemical engineering. So we have a lot of faculty who continuously collaborate with colleagues in other departments in order to tackle not just this type of a problem, but this and other problems that are of interest that chemical engineers alone cannot tackle. So those of you who are undergraduate students, we are looking for good undergraduates. Those of you who are in companies, we do have external PhDs with R&D organizations and companies in India. Okay, so let us now come to a little bit more core part of my talk. So this is the overall view of CCUS. Okay, so CCUS comprises of capture. Okay, capture is of two parts: direct capture from air. Air has approximately 400 ppm CO2. So you want to capture CO2 from very dilute conditions. Okay, point source capture, for example, from flue gases, you have about 10 to 18% concentration of CO2, but you also have water present, you have NOx, you have SOx, and so on. Okay, so you need to be able to capture CO2 in presence of other acid gases. Over here, you need to be able to capture CO2 when CO2 is highly dilute. Okay, so challenges are slightly different, and therefore solutions are likely to be slightly different. Once you capture the CO2, you will transport it, okay, and transported CO2 can be utilized. Okay, three broad ways of utilization. One is utilization in, for example, enhanced oil recovery. You take CO2, you inject it into reservoirs, get fuel out. That's one. Other way is catalytic or thermocatalytic conversion. The third way is electro or photocatalytic conversion. Use light or electricity in order to convert CO2, or you use heat and catalyst in order to convert CO2. CO2 can be converted to fuels, and then you can have circular economy. Circular economy is circular only in material, it is not circular in energy. Okay, if it were circular in energy, you will have a perpetual motion machine, which is not allowed by thermodynamic principles. Okay, please remember, you can violate a lot of other things. You can maybe even violate laws of God, but you cannot violate laws of thermodynamics. Okay, so it's circular in carbon. Okay, which basically means the total amount of carbon gets captured, converted to fuel, which is then burned and then get converted back to CO2. That CO2 again gets captured. So it's circular in carbon. It is may or may not be circular in hydrogen. It is definitely not circular in energy. Okay, and finally, yeah, sequestration, and again then the non-conversion way of utilizing CO2 is also a way for sequestering it. You can take CO2, pump it into reservoirs. If those reservoirs are, for example, have fuel like EOR and so on, you get that fuel and CO2 gets sequestered, or you can pump CO2 either as hydrates or under the earth or under the seabed in order to store it for a larger period of time. Okay, so this is I think previous and this slide again Professor Rajneesh would have talked about it. I have stolen these slides from him. So overall what I'm going to talk about with respect to CO2 today, CO2 capture today, is pressure swing adsorption, temperature swing adsorption, but not really pressure swing and temperature swing, but a material that we are interested in, metal organic framework based material that we are interested in. That's what I'm going to talk about in the next 10 minutes, and thereafter I'm going to talk about CO2 conversion used to methane and methanol. Okay, so that's the next thing that I'm going to talk about, is to convert CO2 to methanol. Doesn't matter where hydrogen comes from for us. We'll assume, Harry Potter magically gives us hydrogen. Okay, and then we will use that hydrogen. Okay, so that's what I'm going to talk about in the next 20 minutes or next 15 minutes. Okay, I'll try to relate it to more chemical engineering principles, more undergraduate chemical engineering principles, because just the previous semester I taught a chemical reaction engineering course to PG students, so it's something that I would like to relate it to. Okay, so CO2 capture in MOFs, specifically we are interested in what is called as flexible structure MOFs. Okay, you have heard of zeolites? Yes, activated carbon. Now these materials are at the molecular level rigid materials. Okay, MOFs on the other hand, or specifically the MOFs that we are interested in, are called soft crystalline solids, which basically means, so think of MOF like a sponge. Okay, water goes in, that water sponge is able to soak up the water, and it might expand a little bit with respect to water, on soaking of water. Okay, however, all of these expansions and everything happen at a molecular level. You do not see those effects at the macroscopic level. If your sponge expands, you probably are able to see it at a macro level as well. Okay, but these MOF materials, there is no morphological change at the macroscopic or visible to our eye level. It's only when we probe it using X-rays, that's when we are able to see more changes at the molecular configurations. Okay, we are interested in trying to use these changes. So let's say we have a mixture of gases, so let's say CO2 and methane that comes in, or CO2 and nitrogen that comes in. What happens is, in presence of CO2, this particular material might expand. Okay, there's a behavior called gate opening. Okay, think about it that this is a palace and there are, you know, dwarpals or watchmen or whatever, soldiers waiting on the door of the palace. Okay, you see methane, no, I'm not going to allow you. Okay, you see CO2, please go. Okay, that's how these materials behave. Okay, why? We don't know yet, but what happens over there is CO2 starts interacting with the organic linkers. The O in MOF stands for organic. It interacts with those organic linkers and makes some morphological changes, which allows CO2 to enter the pores. Okay, what this cartoon shows is actual structure, actual crystal structure of a closed pore and open pore. It's the exact same material. Okay, one is with CO2 not in the pores, the second is when CO2 gets inside the pores, and it does change somewhat. Okay, and if it has captured CO2, it has allowed methane to just leave. Okay, so we have looked at various different MOFs. The idea of MOFs is that there is a metal center and then there is a linker. Okay, so the metal center and the linker are going, so all of these are metals, okay, and these are all linkers. This that you see is a large pore, this is a small pore that is present inside inside the MOF. Now this particular MOF has kind of small pores on the surface, slightly larger pore inside, so the molecules can't come in until the watchmen open the door for them. Once the door is open, these guys, the CO2 goes in. Okay, CO2 is a relatively fat molecule. It will push its way and it will expand the larger pore, the yellow pore that you see over here. Okay, so that's how this happens. The ZIF that I talked about, the ZIF is a family of MOFs. It's called zeolitic imidazolate framework. Zeolitic because it looks like a zeolite, imidazolate because the organic linker that is used is imidazole linkers, and this is one of the examples is ZIF 7, it uses benzimidazole, and we have looked at various other ZIFs as well. Okay, so you have heard of Langmuir isotherm? Yeah, all of you? Okay, this is a typical Langmuir isotherm. The isotherm that you see over here is a typical Langmuir isotherm, okay, or type 1 type of an isotherm. Okay, so it goes and it increases steadily. Okay, this is an S-shaped isotherm that these flexible materials show. Okay, so what happens is when this is in the closed pore structure, okay, there is hardly any adsorption. Okay, when it goes from closed pore to open pore structure, there is a big jump in the amount that it absorbs. Okay, so you can almost think of as two different materials. One material does not absorb CO2, one material absorbs CO2, and magically, thanks to our friend Harry Potter, it goes from one type of a material to another material. Okay, you can think of it or imagine it like that. Of course, it doesn't exactly work like that. It works because of morphological changes that happen outside the structure. Okay, so what does this mean is that if you adsorb at this pressure and desorb at this pressure with a fairly small change in the pressure, or with literally just 5 degrees Celsius increase in temperature, you can desorb almost all the CO2 that you had adsorbed. Okay, that's the positive thing about this material. Okay, however, the potential negative things is one, what is called as a slip off. The other thing is that the morphological changes take time. So when it comes to adsorption, there's only one kinetics, that's the kinetics of adsorption. When it comes to adsorption on this flexible linker morphs, okay, there is kinetics of structure change and then there is kinetics of adsorption. Okay, so those are the two challenges that we are really interested in. We don't really know how to address the latter challenge. How to measure also, we don't yet know how to measure the time taken for the morphological change to happen. We can do it under equilibrium. We cannot yet do it under kinetically relevant condition. And this is an actual isotherm. Instead of kPa, this is in bar, 0.4 bar, 0.6 bar, 0.8 bar. Okay, so literally if we have this particular material, okay, it will adsorb all of CO2 at 0.8 bar and desorb most of it at 0.3 bar. With literally 0.5 bar change in pressure, we can desorb all of the CO2 that we had adsorbed. Okay, and this is what is called as in situ XRD, where we track how the structure changes, and this is just showing how the structure changes at various pressure points. Okay, this is all equilibrium data. That means each of these curves is obtained after waiting for half an hour. What we want to do is to be able to do it, every half a minute, every 1 minute. We don't know how to do it as of today. Okay. What we also found is that the flexibility of these structures is dependent on the crystal size, and we were able to manage the crystal size so that we get a very steep curve. Okay, which means at 0.6 bar we can adsorb, at 0.3 bar we can desorb. Okay, so with a fairly small change in the pressure of CO2, we can do adsorption and desorption. Okay, and the hope is that if we can do that, and if the structure changes are fast enough, okay, the capacity of this material might be low, but we might be cycle 100 times in an hour and adsorb, desorb very quickly. Okay, so that's why this is interesting. Okay, and we ran this for various different fluids, gases and vapors, and this has an interesting property. Molecule like hydrogen or molecule like methane, this material won't admit, but it might still admit a molecule as large as N-heptane. It's a beautiful material that way. So think of how large N-heptane is, think of how small comparatively nitrogen is, but it happily admits N-heptane, but it does not admit nitrogen. Okay, or not at least not until 35 bar pressure. Sorry? Let's not touch water vapor when it comes to moths. Yes, water vapor is a challenge. Okay, yes, so this one will. I wish nobody asked a question like that, but yes, I mean water is a challenge. Yes, water is a challenge because luckily on this one has a hydrophobic group, and therefore CO2 adsorbs earlier than water. Okay, but water interferes with the ability of this material to absorb CO2. Okay, very recently, literally 4 months back, Yagi group from Berkeley published recent work where presence of water enhances the ability of the newest MOF to capture CO2. Okay, probably the first known MOF where CO2 capture is enhanced by the presence of water. Okay, and again, I mean, coming back to compromises, the linker is so expensive and so difficult to make that if we want to really commercialize it, it's going to be a challenge. And literally there might be 5 groups in the entire world who have the ability to do that. But yeah, but it's a very interesting material. Okay, the other thing, and I won't go into the details of this, but the other thing I want to compare is look at how low is the CO2 adsorption for the ZIF7 compared to ZIF8. Okay, we still prefer ZIF7 for this S-shaped isotherm. That's really what interests us. I don't care whether it is able to solve the problem or not as of today. Why? Because we are interested in understanding these materials so that in future we can make better materials. Okay, so this material is definitely not going to solve the problem, but it's going to hopefully improve our understanding to make materials that can potentially be used as the next generation materials to solve the problem. Okay, so although the total CO2 capacity is about a third of a reasonable material, that is ZIF8, okay, still we prefer this. Why? Because for ZIF8 to desorb all the CO2 that it has absorbed, you need to change the pressure by say 5 bar, 6 bar and so on, whereas for this material with 0.3, 0.4 bar change in the pressure, you can desorb all the CO2 that you have absorbed. Okay, the other advantage that this gives you is this is what is known as selectivity. So what's the fraction of CO2 in the adsorbed phase divided by the fraction of CO2 in the gas phase. Okay, and for ZIF7 material, for example, for this material under at 30 bar pressure under conditions that are relevant for flue gas, you have almost, the selectivity ratio is almost 30. Okay, that means you have 30 times more CO2 captured compared to how much CO2 is there in the gas phase. Okay, so yeah, so summary is that we are, yeah, I mean, these are challenging problems, but what we are in our group, what we are interested in is trying to understand these very interesting materials called MOFs from an engineering perspective, and how we can use these materials in order to capture CO2. Okay, I don't have too much time, so I'll quickly go over another concepts, and that is combining heat exchangers with reactors. Okay, that means if for those of you who are chemical engineers, heat transfer, fundamentals of heat transfer combining with chemical reaction engineering into one reactor. That's what process intensification means. You combine multiple unit operations in one single reactor. Okay, so what we are going to do is we are going to carry out reactions in heat exchangers. Okay, it could be a counter current heat exchanger where you have flow in counter current direction, or a U-bend where the flow goes in this direction and then bends over. Okay, there will be heat transfer that is going to take place if there is an exothermic or an endothermic reaction between the two channels of the heat exchanger. Okay, and then there are other reactors that are very well known also. Okay, There is this concept in combustion called excess enthalpy. Okay, let's think about a burner like a Bunsen burner. Okay, if you start at an inlet temperature over here, okay, the amount of temperature rise is going to be delta T adiabatic. Okay, you would have done this in your CRE. Delta T adiabatic is minus delta H divided by Q rho Cp. Q is flow rate, rho is density, Cp is specific heat. That's delta T. It's a thermodynamic property. Okay, if you have a fuel that will combust, your delta T is fixed for a particular inlet composition. Okay, the temperature by which, for complete conversion, the temperature by which the temperature will rise, let's say in a Bunsen burner, is going to be exactly equal to delta T adiabatic if it's an adiabatic reactor. Okay, but if it is reaction in heat exchangers, okay, we get an interesting behavior. We get temperature that exceeds the adiabatic temperature rise. Why does it do that? Because at exit the burned gas transfers heat to the unburned gas. So the reaction does not start at room temperature, but the reaction starts at say 150 degrees Celsius. So the delta T adiabatic goes from 150 degrees Celsius to plus delta T adiabatic. So the final rise in temperature will be say 120 degrees more than what you had observed earlier. That's the idea behind excess enthalpy combustion. Okay, but the exit temperature has to be equal to delta T adiabatic. Why? First semester or first year chemical engineering course, process calculations. You put a box around that reactor, doesn't matter what happens inside the reactor, right? Energy balance and mass balance have to satisfy in and out. Okay, so what do you think will happen if you cut this reactor over here? Will you get super adiabatic conditions? So what happens actually is that the temperature will either move leftwards, so that the end point is going to still be equal to T adiabatic, or it will move rightwards. If it moves rightwards, then the flame will not be stable. One of the two will happen. Okay, the latter is what is known as blowout. Okay, that's an instability in this in these systems. Okay, so that's what happens. Again, thermodynamics and process calculations, the first two courses in your undergraduate curriculum will not be violated. Okay, when I was a student, there was this big deal that was being made about fuel cells violate the second law of thermodynamics. They never did. Okay, these laws of thermodynamics as of today and in the foreseeable future will not be violated. The deck is stacked very high for anyone who claims that laws of thermodynamics have been violated, because that researcher will have to fight 150 plus years of evidence. Okay, and that's how science works. It doesn't mean so. Everything in science is contingent upon one experiment or one theory which is reproducible that shows a counter example. Okay, so none of it is this is set in stone and never. Yeah, if we find an example which violates, yes. Example, nuclear fission, right? Until that time, mass was conserved, but then it's E equal to mc square happened, right? So anyway, that's science. So if things cannot change, then that's not science. So the important thing about science is falsifiability. Can you come up with an experiment that will disprove whatever we hold dear to the heart? Okay, anyway, so what we try to do is to do the reaction in a heat exchanger. Okay, so the heat exchanger that we had is a U-bend heat exchanger, okay, where this is going to be the flow, and we compare it with parallel channel heat exchanger. because both the channels are exactly equivalent, there is not going to be any heat transfer between the top and the bottom channels in the second example. Okay, what happens if you have U bend? Your inlet is going to be cold, okay, but reaction takes place, the temperature goes up due to reaction, okay, then the temperature stabilizes, U-turn happens, and as the products are going out, there is heat transfer taking place from the hot products to the cold incoming stream, okay. The interesting thing that happens, now methane, CO2 to methane or CO2 to methanol are mildly exothermic reactions. Le Chatelier's principle, thermodynamics is preferred at lower temperatures, kinetics preferred at higher temperatures, okay. So what happens is that initially there is no reaction, why? Temperature is too low, then there is very high reaction because the temperature is high enough for reaction to take place, equilibrium is reached, there is hardly any reaction taking place after equilibrium is reached. Now when the temperature cools down, okay, you get a thermodynamic bump, you get reaction happening once again, okay. What I am plotting over here is if you have a U bend like this, okay, if I open this at this point and I plot it in this direction, so this from 0 to 0.5 flow is in this direction, from 0.5 to 1 the flow is in opposite direction, that is what I am plotting, okay. So if you have a U bend like this, I am just opening it up while plotting, okay, and because of the reduction in temperature over here, because of Le Chatelier principle, you have this reaction, because of this reaction you have methane that is formed, okay. Fun fact, this is not new, as chemical engineers we knew this from 1960s and 70s, okay. Companies like Casal, ICI and so on had come up with these reactors for methanol synthesis, for ammonia synthesis and so on. In 1990s and early 2000s, Eigenberger and co-workers called this as autothermal fixed bed concepts, where you do these reactions in heat exchanger like assemblies. We just need to reimagine those same principles for present day challenges, okay. This is something that I have taken from the CRE book by Froment and Bischoff, okay. The book was first published I believe in 1983. This is a figure from first version of the book. So we knew about these concepts, okay, but not in today's context. Just knowing about the concepts is not enough, we need to revisit them in today's context with today's materials to address today's challenges, okay. That is going to be my last slide. I won't talk about rest of it, I leave you with that. So the main message that I wanted to talk about is all just general. Main message that I want to talk about is the following. The challenges that face us, okay, are not easy challenges, and that's all the more reason to focus our energies in coming together and solving those challenges. The rules of chemistry and physics and engineering, the laws of chemistry and physics and engineering remain the same, okay. We need to ensure that the laws, that the solutions that we come up with or that we imagine don't violate those laws. The third thing is the whole body of knowledge that we have generated over the last 30, 40, 50, 60 years, okay, there is a lot of opportunity to revisit those, but to reimagine them in present day context. That is what a lot of our research and our endeavor is focused on, okay. So that I would like to end my talk, and if there are any questions I will be happy to take.